Resistors in series and in parallel. First, let us learn resistors in series. Here, three resistors are connected end to end. The equivalent circuit is given here on the right hand side. The single resistance Rs can effectively replaces the combination of R1, R2 and R3 in series combination. When two or more resistances R1, R2 and R3 are connected end to end, they are said to be in series. As the current I through each resistance is same, then according to Ohm's law says V equals IR. So I is constant, so V becomes proportional to R. So the potential difference across each resistance is different provided resistances are different. V1, V2 and V3 are the potential differences between the ends of the resistances R1, R2 and R3. Rs is the equivalent resistance of the three resistance in series combination. V is the total or applied potential difference. So let us go to the concept. To find the equivalent resistance, we equate total potential difference across the combination to sum of the potential difference across the individual resistances. So V equals V1 plus V2 plus V3. Let us substitute V as IRs equals V1 as IR1, V2 as IR2, V3 as IR3, because the current is same in all three resistances because they are in series combination. Let us take I common in the right hand side and cancel with the I in the left hand side. So final equation is Rs equals R1 plus R2 plus R3. Let us learn resistors in parallel. Here three resistors are connected in parallel along with the battery. The equivalent circuit for it. Here you have Rp, which is effectively replaces the parallel combinations of R1, R2 and R3. When one end of all resistances R1, R2 and R3 is connected to one point and another end of all resistances is connected to the second point, then this comes under parallel connection. As the potential difference V across each resistance is same, then according to Ohm's law, V equals IR. As V is same, I proportional to 1 by R. The current in each resistance is different provided resistance are different. To find the equivalent resistance, we equate total current across the combination to sum of the currents across individual resistances. I1, I2 and I3 are the currents flowing through the resistances R1, R2 and R3. Please look at the diagram. Rp is the equivalent resistance of three resistances in parallel combination. I is the total current. So I can say that I equals I1 plus I2 plus I3. I equals I1 plus I2 plus I3. So let us substitute what is I. It is V by Rp. What is I1? V by R1. What is I2? It is V by R2. What is I3? V by R3. We are using Ohm's law here. As the potential difference across all the resistances are same, correct? The V on left hand side and right hand side get cancelled. So we get 1 by Rp equals 1 by R1 plus 1 by R2 plus 1 by R3. Tips and tricks for shortcuts. Resistors in series. In case of resistance in series, if one resistance gets open, the current in the whole circuit becomes zero. If one resistance R1 gets open, the current cannot go to R2, cannot go to R3. Decoration of lightning in festivals is an example of series combination. Same current flows through each resistances, so we can say that V proportional to R. Power consumed or in the ratio of their resistances, P proportional to R. In series combination, power consumed are in the ratio of their resistances. P1 is to P2 is to P3 equals R1 is to R2 is to R3. If n identical resistances are connected in series, then the effective resistance Rs equals n times R. Equivalent resistance is greater than the larger value of the resistances in the combination. Rs must be greater than the maximum of R1, R2 or R3. There are three resistances, 2 ohms, 3 ohms and 4 ohms. All these three resistances are connected in series, then the effective resistance will be greater than the highest value, that is 4 ohms. If n identical resistances are connected in series, then the potential difference, the individual potential difference across each resistance equals V by N. For two resistances in series, Rs equals R1 plus R2. Potential difference across any resistances, V prime equals R prime by Rs into V. That is, given resistance by total resistance multiplies the applied potential. This is what the potential difference across individual resistances. So you have to take a given resistance divided by total resistance multiplies V. Let us now work with V1. For V1, the given resistance is R1 divided by total resistance is R1 plus R2 multiplies V. We get V2, the given resistance is R2 divided by R1 plus R2, that is a total resistance multiplies V. This is the circuit for it. It comes very late. Resistors in parallel. Here there is a circuit, the equivalent circuit is given. In case of resistance in parallel, if one resistance gets opened, the current still exists in other resistances. Suppose R1 gets opened, R2, through R2 there is a current, through R3 there is a current. So the bulb glows at R2 and R3, but bulbs does not glow at R1. But that is not the case in series combination. Household appliances connected in parallel grouping. What we have in our household appliances are all connected in parallel combination. Suppose one appliance is failure to work, it gets open, other appliances works well. Same potential difference applied across each resistances, therefore I proportional to 1 by R. More is the resistance, less will be the current, or less is the resistance, more will be the current. Power consumed are in the reverse ratio of their resistances. This is for a parallel combination. P proportional to 1 by R. So we can say P1 is to P2 is to P3 equals 1 by R1 is to 1 by R2 is to 1 by R3. If n identical resistances are connected in parallel, Rp equals R by N. The effective resistance will be equal to R by N. If n identical resistances are connected in parallel, then Rp, the effective resistance, will be less than the least value of the individual resistances. Equivalent resistance is smaller than the lesser value of the resistance in the combination. If n identical resistances are connected in parallel, I prime equals I by N. I prime is the current through an individual resistance, that will be equal to the total current by the number of resistors connected in parallel. Now two resistances are connected in parallel. For two resistances in parallel, the Rp will be R1 R2 divided by R1 plus R2. This is the better formula. So on the numerator you have the multiplication of R1 R2. In the denominator you have addition of R1 and R2. Current through any individual resistances, I prime equals resistance of the opposite branch divided by total resistance into total current. So let us go with I1. That will be equal to R2 divided by R1 plus R2 multiplies I. I2 equals the resistance in the opposite arm will be R1 divided by R1 plus R2 into I. Thank you, children.